Hello everybody. So today I will talk about the system design of Tinder and I will do the deep dives. So today I will talk about these three topics: low latency on stack loading and strong consistency on matches and scalability. So let me get started with the first one. So low latency on stack loading. So I will talk specifically about this part. So I've already introduced the stack generation daily job. So every night for each user, the stack of profiles which are displayed to that user is generated and stored in the database. The reason why I have to do that is obviously if we try to generate the stack of profiles when user opens the app, it can take so much time and user maybe have to wait for start swiping. Yeah. So I introduced this text generation data job. And now what I'd like to mention is, so um, about this query to create the, stack, I think the most important and interesting part is about the um, filtering by the condition. So user specifies the max distance, and according to that distance, I have to filter the users. So I use the PostGIS extension here. So with this point data type, which is two dimension, latitude and longitude, without this PostGIS extension, I can do the search or how should I say, filtering on the 2D plane, like XY plane, but it doesn't take the curve of the Earth into consideration. So what I have to use is the PostGIS extension. So with PostGIS extension, I can use the geolocation index with this point type, and now it, takes the curve of the Earth into the consideration, so I can get the quite, accurate, filtering with the maximum like 10 miles or something. Yeah. And so this one, I mean, the filtering with the location uses the geolocation index. And for others, I can use the filtering. I mean, for other filtering, I can use the B3 index. So, but of course, even if I put the B3 index on the height and raise and max distance or something like that, for each of them, of course, it doesn't work for I mean, or should I say, only one of them is used when there's a filtering. Yeah. So the thing is, yeah. Um. So yeah, but this, which index to be used is determined by the query optimizer of the PostgreSQL. So the query optimizer of the PostgreSQL does the decides which index to be used by the condition of this. Yeah, and also it does the filtering with PostGIS, I mean geolocational index, and all of them are optimized in a smart way by the query optimizer. Yeah. So that's why I can say Postgres is very good at this, scenario. Okay, and actually I have another, option that I use the, let's say, Elasticsearch. So I'm pretty sure this PostgreSQL is good enough, but just I want to mention that Elasticsearch has the geolocation index and also B3 index in the same way. So maybe what I can do is, yeah, you know, send the CDC, which is a there is a worker which consumes the CDC of the PostgreSQL and updates a Elasticsearch index, and this text generation daily job search from this Elasticsearch. Yeah, this is possible, but I don't use it. So probably if I try to use this, I will use this if the text search is necessary. But of course, in Tinder, there isn't the search window or search text window, so I I wouldn't use Elasticsearch in Tinder. So I delete this. But I just wanted to mention this as the another kind of option for geolocation index. Okay, so that about the first, yeah, topic, low latency of stack loading. Okay. Okay, so next I will talk about the strong consistency of matches. So this comes from the non-functional requirement here. Consistency over availability for matching, which means I need a strong consistency for matching. So it's about here. So the current design is swipe service creates a swipe record, and then it checks if there is a kind of reverse swipe from that user who was swiped, and if it does exist, it means that it's a match, so it creates a match record. Yeah, and because I don't want to make the data inconsistency, I do these operations in the same transaction. With this, I can guarantee the atomicity. Yeah. Okay, and I will talk firstly why this can cause the race condition. So typically, user 1 swipes user 2, and what then internally this, user 1. So I will call the process 1. This is the server request handling process. And so process 1 creates the swipe record user 1 to user 2. Then process 1 checks swipe user 2 to 1 and not found. So no match record is created. And then user 2, when user 2 makes a swipe for user 1, sorry. So what happens is the process 2 creates a swipe 2 to 1 and check swipe 1 to 2. So this is found. So now process 2 create match 1 and 2. So this is the process. Yeah. The order of event which are where race condition doesn't occur. But let's say user 1 and user 2 swipes each other almost at the same time here. So what happens with this is that process number 1 creates a swipe use 1 to 2, and process number 2 creates a swipe 2 to 1. And because those are, process 1 does this and this in the same transaction, and process 2 does this and this in the same transaction until the um, you know transaction is finished. The internal record of the database is not visible from other transaction process. So let's say process 1 does check swipe to 2 to 1 here, but not found here because this is not committed yet. Same for this, because this is not committed yet. Check 1 to 2 is not found, and this doesn't occur. And now process 1 commit, and process 2 also commit and finish the transaction. So this is the order where the race condition occurs. Okay, so now I explained in which case race condition occurs, and now I will talk how I can avoid this. So the fundamental problem is, of course, process 1 and 2 almost does it in the same order, and each operation, operations are interweaved to each other. So the first solution I can use is use the PostgreSQL's isolation level serializable. So this is the isolation level about the transaction. So with this serializable isolation level, each transaction is, handled one by one. Yeah. So in a serializable way, literally. So this is not linearizable, so it doesn't mean the next transaction cannot be begin until the last one is finished. Yeah. So it is possible that they overlap in a sense, but still, they can be interpreted as they occurred one by one. So that's the serializable level of the isolation. So with this, obviously this doesn't occur because process 1's whole operation is done first, and then user 2's whole operations are done next. Yeah, but there is a problem here. So there is a performance. So with this isolation level, every transaction which is thrown to this database has to wait in a kind of waiting queue. So that query may be the one which is not related to this one, this swipe. Maybe of course, here there is a query that reads the list of matches. Even for that query, it has to wait in the queue. So this is quite not performant, but a performance. So I don't use this one. So the next solution is using the pessimistic row lock. And also, of course, we have the optimistic concurrency lock. Yeah. So I have these two options too. So I will talk about the pessimistic row lock first. So this is something like so the query, when it reads from the recode, it uses the select for update statement. So with this, what happens is that it reads the recode, and that record is locked by that query, and it commits the transaction. So after locking that record, that process with that record is not updated. So where is it? And let's say each process does it. Each process tries to lock the record first, which means that for that record, all the operations are serializable. Yeah. Because yeah, as I said, each transaction tries to get the lock of this record. Yeah. So this is the pessimistic row lock. But in this case, still in this table schema, I cannot use the pessimistic row lock because there isn't, before swiping, or I should say, it's a bit complicated, but user 1 is interested in the record of swipe 2 to 1, and user 2 is interested in the record of user 1 to 2, the opposite one for each. So it not, best, it doesn't work with the row lock with that. So what I can do is think of this as a dual swipe record. So user 1 to swipe from user 1 to 2 and swipe from user 2 to 1 are put and stored into the same record. So this can be Boolean, true or false or no, null. Same for this. Yeah. And maybe we need the timestamp when user 1 likes user 2 or something like that. But the core, part is this one. And we, put the constraint that, and I will as check constraint. So I add this check constraint here to make sure that user 2's ID is larger than user 1's ID. Okay. So this is a dual swipe record. So with this, when user 1 tries to swipe, it locks this record, and now it checks user 2 liked user 1 already, or maybe maybe first we should write it. So firstly, user 1 update user 1 likes user 2 boolean, and then after that it checks user 2 liked user 1, and if it is true, it's a match, so creates a match record and finish the transaction. Now user 2, if user 2 swipes the user 1 just after that, it can now get the lock of this dual swipe and then check and find that user 1 liked user 2. So match record is created. Sorry, in the case of user 1, match record was not created. So now user 2 creates the match record and finish the transaction. So in this way, I can use the row lock of dual swipe record, and with that, the query which came after later has to wait in the waiting queue. But this waiting queue is this row level. So this row's queue. Yeah. And when the first query is done and committed, now the second one gets the lock, and yeah, that's the operation. Okay, so this is the pessimistic row lock approach. So this is performance-wise good. I mean, this is performance-wise good because the query has to wait in the queue, but it is only for the that record. And one more thing I can say is because the users who are interested in this dual swipe is only user 1 and user 2 in this case. Or I should say user ID 1 and user ID 2. So at max, the length of the waiting queue is only 1. So, the waiting time in the queue isn't a big issue in this case. So this sounds pretty good. And maybe one more thing I have to mention about this approach is who creates this dual swipe record. So I can use something like insert, okay. And to avoid the same dual swipe record to be created in a duplicated way, I add unique constraint. And I add this unique constraint, and every time there is a swipe, the process tries to create this dual swipe if it's not created yet. So it can be like insert into dual swipe record user ID 1, user ID 2, and if there is only the record, do nothing. So that query is thrown first before starting the transaction to lock the select update. Yeah. So that's the approach I can take to create the dual swipe record. Okay. So I will talk about the solution number 3, optimistic concurrency lock. So this is something, okay, I will hand wave this approach because actually solution 2 is good enough. But basically what happens is that I actually use a dual swipe record in this case too, and I add the version key, something like version key. And there are two, user run process and user two process who want to take a look at dual swipe. So firstly, the process takes a look at the latest version key, let's say 3. And let's say user 1 and user 2 process reads the version key 3 almost at the same time. And next, each process throws a query with update the user 1 likes user 2 or user 2 likes user 1 value and version key to be 4, which is 3 plus 1, where version key is current 3. So each transaction, each process throws that query. And then only the first one can update the record. Because after the first one is updated, version key becomes 4. And now it isn't filtered with the where version key is 3 condition. So the latter one fails to update. Now that process has to retry. Retry means that reads the version key again, which is 4, and tries to update the record with version key 5 and condition where version key is 4. So this one now succeeds, and which means that the router one could update it, and also he can see that either mutual swipe. So that router process creates a match record. Yeah. So this is the optimistic concurrency rock. So this works, but I actually want to go with pessimistic row rock this time because, as I said, the waiting queue is not so wrong, not so long. So pessimistic row rock is good enough, and also with pessimistic row rock, we don't have to write the complicated process about with the version key. So, and also we don't have to create the version key column here. So I will go with the pessimistic row rock. Okay, so yeah, that's it. So now I talk about the strong consistency of matches. But actually, I want to mention that we don't have to persist in the strong consistency here. So another approach here is I accept that this race condition occurs, and you know I accept that the match is not created immediately when user 1 and user 2 swipe each other almost at the same time. But instead, I introduce the, let's say, hourly cron job here. So this takes a look at the swipe record, and then if there is a missing match, it creates a match record here. And now what happens is that that match is notified to both of these users. So which means that both of these two users, user 1 and user 2, are notified with the push notification maybe after maybe 20 or 30 minutes, or maybe up to an hour later, even though they swiped each other and matched immediately. Yeah, theoretically. So this is actually the possible, yeah, approach too. So I wanted to just mention it, but yeah, I think it totally depends on the product decision. But I can say the mutual match is very rare. So yeah, personally, I think conservation job is good enough. Yeah, but yeah, even with this strong consistency guarantee, actually this is not so complicated. So maybe yeah, both of them are fine. Okay. Okay, so now I will talk about the third topic, scalability. Scalable to 20 million daily active users. So I will talk about this from two perspectives. The first one is the scalability about the throughput. And secondary, I will talk about the scalability in terms of the storage. So I will go with the throughput. So when I take a look at this, these APIs, definitely the most heavy one is Swipe API, because update user API, this is quite infrequent. I think when I'm using the dating app, I don't update my profile once a day, maybe once every week or something. Yeah, so this is not so, you know, heavy, intensive. For this upload location API, this sounds like intensive, right? Intensive, but actually not, because in Tinder, the location can be a kind of rough location. So in case of the, let's say, Uber's driver has to be the location has to be very accurate. So it has to be updated maybe every 5 seconds or 10 seconds. But for the Tinder, this is used for the filtering of the distance. And distance can be, distance is like every 1 mile or something. 1 mile, 2 mile, 3 mile. So we never take care it is 2.56 miles away or not as the condition. Which means that, let's say I go to the convenience store in the, to get something. The front end doesn't have to update the location. So we can set the kind of threshold, like if the user moves, let's say 1 mile from the last location, the front end has to update, the location with API call. So with that, I'm pretty sure this is not heavy loaded for server. Maybe this is called, maybe, I don't know. Yeah, maybe once an hour. Yeah, or something on average. So this is not so heavy. And for get for profile tag, this is called once every day. So this is not so heavy. For swipe API, this can be heavy because user swipes many users a day. So let's say half of the user swipes, opens the app, and let's say each user up swipes 20 profiles a day. So in this case, in a day, there should be 200 million requests per day. So in a day, because one day is 10 to the 5 seconds, it should be 200 requests per sec. So actually not so heavy loaded for server. Yeah. No, sorry, 2K. So 2K requests per sec can be handled by single PostgreSQL instance, because typically PostgreSQL can handle maybe 10K requests per sec for write request. So yeah, this is totally fine. Yeah. Okay. So that's it. And yeah, for other layer, API gateway, this is actually the cluster of servers. So this internally scales. And for this service, it can be scaled horizontally, horizontal scaling, because each request is stateless. So I can scale out. So I can use, let's say, AWS auto scaling with a threshold of CPU usage or memory usage or something like that. Yeah, so this is totally fine. Okay. And oh, of course, tag generation daily job. This can be quite heavy. Yeah, because it makes a query to the server. Maybe I should think about this. So let's say this text generation daily job makes a query for one user one time. So this means that there should be how many queries? Because there are 20 million daily active users. It has to create 20 million users stack profile, so recommendation in a day. So 20 million queries per day. So this is 200 query per second. Yeah. So this is not so heavy loading, but to be honest, I have a bit concerns that this query is keep, loading the primary DB. And because this is completely a read query, I think I can use the read replica and make sure that this stack generation daily job makes a query to the read replica instance. Yeah. So for this, the write, queries are handled by the primary DB, and yeah, we can make sure that write query is not, affected by the stack generation daily job. Okay, so I will talk about the storage. So storage wise, let me see. Actually, because when there are 20 million users, this user table should not be too, problem. My concern is maybe stack profile, because this is refreshed every night, but number of records should be 20 million times 30 or something. And for DL swipe, this is also a bit concern because there are 20 million requests per day. So exactly, I mean, in the worst case, if there isn't any mutual swipe, 200 million requests are created in a day, and the number of records is keep increasing. Yeah, for much, this is also the concern, but the number wise, it is smaller than dual swipe, so I will take a look at dual swipe. So I will quickly talk about the user and also stack profile and also dual swipe. So user wise, because there are 20 million daily active users, let's say in total there are 50 daily active users million. Oh, sorry, I should have used this number here too. So total 50 million. Yeah. So let's say each user has 1 kilobyte of record, then this becomes 50 terabytes. Yeah, this is 10 to the 7 and the 10. So kilo mega gig, wait, 50 million users and each is 1 kilobyte megabyte kilo. So this is only 50 gigabytes. Okay, it's totally fine in to be stored in the PostgreSQL. For stack profile, we need 50 million users, and each user, let's say, for each user, let's say I create 50 records, and for this stack profile, the table should be a little bit smaller, like 100 byte. So this should be 5 kilobytes, so 250 gigabytes. This is also totally fine to be stored in the PostgreSQL, because nowadays, like OverDB in AWS can store 512 terabytes. So this is totally fine. And for dual swipe record, um, so as I said, in a day, there should be 20 million daily active users, and let's say each user swipes 20, and let's say each record is 100 byte. In that case, so this should be 4 times 10 to the 1, 8, 10 byte. So this is kilo mega giga, 40 gigabytes a day. Yeah, and this increases. But actually, in Tinder, many users deactivate their account, let's say in half a month, half a year. So let's say on average, user keeps the profile for 3 months, like 100 days. Yeah. So this should be 4 terabyte. So this dual swipe record, yeah, 4 terabyte. Yeah. Also, this is completely storable in PostgreSQL order or PostgreSQL. Yeah. And of course, when user deactivate, we delete the existing record of the users and also dual swipe and matches. So yeah, this dual swipe, you know, for this dual swipe, it's up to 4 terabytes. Okay, so actually, so I mean, scalability wise, this system is not so difficult. Yeah, it's easy. So I will talk about a few follow-up questions here. So what if user updates the profile or just a preference or location, and in that case, the stock profile record can be updated. Yeah. So if I completely change the, you know, profile, I mean preference, the system has to show the completely different users from, yeah, the users pre-calculated last night. So I think the easiest solution for this is kind of pushing back as a product. So I've seen the kind of statement like, if you update the profile preference, it takes a few days until it is reflected to the users who were suggested to you. So I think this is the easiest approach. Or what I can do is, if I'd like to, handle this for real quick, I can use a change data capture. So when user updates the profile, or maybe location is completely updated, the change data capture from this database is consumed by some worker, and then, so I mean, this is a worker, so this is the stack upload which is a refresh worker. So now this worker triggers the stack generation job to, update the stack profile created to here. Okay, so this is what happens when user updates the preference. But if he update his own profile, let's say race or maybe height, so of course it's not possible. Realistic, but let's say I don't come up. Yeah, but maybe hobby which is selectable enum or something like that. So in that case, it has to be, um, you know, invalidated in this tag profile table. So I think there are two approaches here. So for these profiles attributes, of course, it is possible to use the change data capture to invalidate these records in the stack profile. But another solution is doing the final validation in the front end. So front end does the validation finally before the profile is shown to the user. So I can add this front-end validation, and also I will pre-calculate the stack profile with some buffer. So let's say we'd like to show 30 new users every day. In that case, stack generation daily job can create maybe 50 suggested profiles. And front-end skips invalidated ones. And yeah, maybe front-end request 30 records first, but is there maybe 5 invalid, which means that the profile has been updated. Such users are, if 5 users exist, it requests backend to fetch 5 more stack profiles. Yeah. So that's a kind of approach I can take here. Okay. Okay, so that being said, I finished my today's system design practice. Yeah. Okay, bye. Thank you.